Every year since 2018, astronomers have spotted a mysterious blue flash in the sky. It is one of the brightest phenomena in the universe, an explosion that makes the average supernova look like a faintly lit candle in the distance. Some have been spotted closer to us, and others billions of light years away. They look similar enough to one another, but no one knows what they are or what causes them. Through rigorous observation and analysis, astronomers began decoding a pattern and formulating a tentative but plausible theory, until in 2023 they saw something that left them completely baffled. These explosions are called luminous fast blue optical transients, and there's simply nothing else like them out there. I'm Alex McColgan and you're watching Astrum. Join me today as we dive into the mystery of space's brightest explosions, how they were discovered, and why they keep stumping scientists again and again. Being such a recently discovered event, the data we have on luminous fast blue optical transients, or LF-bots for short, is minimal. The first LF-bot ever detected was identified just 6 years ago in 2018, and we've only witnessed a handful of them since. As so little is known about them, it makes agreeing on a universal definition a little tricky. For now, what scientists do all agree on are some common characteristics these LF-bots seem to share. So far, they all display a predominantly blue emission, very high optical luminosity, and being bright in X-rays, ultraviolets, and radio waves. They are also very fast, as their name indicates. LF-bots go off like a cosmic camera flash. They reach peak brightness and then dim very rapidly, usually in the space of hours or days. As you might know, a supernova follows the same pattern of brightening and then dimming. But this dimming takes weeks or months. This short-lived nature of LF-bots makes them difficult to spot and study. So, how did we manage to capture such an elusive event? NASA's Atlas HKO telescope in Hawaii is part of an early asteroid impact warning system that scans the entire sky several times a night for moving objects. On the 16th of June 2018, Atlas HKO was performing its routine scan when it captured something very unusual, a flash 100 times brighter than a regular supernova that disappeared within days. The scramble was on. Scientists immediately started analyzing the data to understand what they'd seen. They pinpointed the explosion as coming from the Hercules constellation, some 180 million light years away. Officially designated AT 2018 Cow, the event was affectionately nicknamed the Cow after the last 3 letters in its name. Once located, it was quickly classified as a Type 1b supernova. This kind of supernova, also known as a core collapse explosion, is formed when massive stars collapse under their own gravity. But something about this particular explosion didn't quite fit. When taking a closer look at the Cow's emission spectrum, it didn't look very typical for a Type 1b supernova. It had unusually broad emission lines and very weak helium lines. Scientists thought it appeared more reminiscent of a Type 1c BL supernova, and so was quickly reclassified. However, the more scientists pored over the data, the more surprised they were by what they found. Whatever this explosion was, it started to look less and less like a supernova. At least, not the kind of supernova we'd expect. For starters, it appeared out of nowhere. This blast went from inactive to peak luminosity in just a few days. Like we mentioned earlier, supernovae usually take a few months to reach their brightest and dim again at a similar pace. Not only that, it was registered to be 10 to 100 times brighter than an ordinary supernova. Also, Everything about the way it exploded was wrong. When supernovae explode, they tend to release their energy in a spherical shape. We know now that the shockwave sent out after a supernova can be aspherical due to the presence of strong magnetic fields, which can distort the shape of the initial blast. However, upon closer inspection, this mystery explosion did not even explode spherically. The researchers themselves called it the most aspherical explosion ever seen. Soon enough, other theories were being put forward. Some thought the cow could be a monster black hole shedding a passing star. Others suggested it was a supernova that gave birth to a black hole or a neutron star. But let's step back for a moment. It's really hard to draw any conclusions when you only have one of something. As the saying goes, once is an anomaly, twice is a coincidence, and 3 times is a pattern. What researchers really needed was a bigger sample size, more instances of this kind of explosion, so they could compare observations and deduce any patterns that might arise. Luckily, it didn't take long for scientists to get their eyes on a second similar explosion. A few months later, in September 2018, the cosmic camera flashed again. And again, for a 3rd time in 2020. Keeping in the tradition of pulling animal nicknames from the last 3 letters of their official names, we had the beginnings of a LF bot zodiac. The cow was joined by the koala and the camel. And just like that, they had data on 3 separate LF bot events. They could start hunting for patterns. When analyzing the cow, koala, and camel, one of the first things that stood out to researchers was the location of these events. Even though they all happened in different parts of the universe, each blast was registered as coming from inside the spiral arm of a galaxy. At first, this information emboldened the initial theory that LF bots were just a type of core collapse supernova. Let me explain why. The kind of star that causes a core collapse supernova is a massive star, one of the biggest types of stars you can get. And as you know, the bigger the star, the shorter its lifespan. This means that these stars don't get the chance to travel very far before they die. It would make sense then that their supernovae occur very close to the star cluster where they were born. And what part of the galaxy is known for having such clusters? Yep, the spiral arms. The exact place we saw all 3 LF bots. But just as researchers seemed to be making progress, something happened that caught them completely off guard again. Like the Atlas HKO in Hawaii, the Zwicky Transient Facility is a very wide-angle ground-based camera that scans the whole northern sky every 2 days. In 2022, it detected another similar explosion. Except, after the initial blinding flash, this optical transient started behaving rather strangely. Instead of exploding once and fading away in a few days like the other LF bots before it, the so-called Tasmanian Devil continued to produce short-duration bursts far longer than expected. What's more, each of these bursts seemed to be just as bright as the original explosion, which was very strange indeed. The Tasmanian Devil emitted more energy than hundreds of billions of stars like our Sun combined. Researchers were deeply puzzled yet again. It was unlike anything they'd ever seen before in astronomy. Now, I know the skeptics among you may be thinking, Alex, this has got to be due to some kind of technical error, miscalibrated equipment, a fluke in quality control tests, or a simple mathematical mistake. Indeed, the history of science is littered with scientists shouting Eureka at supposed breakthroughs or discoveries, only to be deflated once someone checked their workings. But this is not one of those moments. The data was corroborated by 14 other telescopes around the world. They confirmed that the Tasmanian Devil did in fact pulsate a minimum of 14 times, the total number was likely much higher. Equally surprising, these mega powerful pulses were only minutes apart. It looked to scientists like a star that kept dying and being revived again and again. If that's what it is, the strange phenomenon could provide brand new insight into the life of stars. So far, stellar life cycles have only been studied as snapshots of different stages, never as a continuous process. In short, even though the multiple bursts of light from the Tasmanian Devil were unexpected, there was still reason to suspect these explosions could have been a strange type of supernova, seeing as none of the observations directly violated the core collapse supernova theory. But what came next did. On April 10th, 2023, astronomers picked up yet another big blue explosion with all the same characteristics as their LF-bot zodiac relatives. Except this one was not even close to where it was supposed to be. Unlike all the other LF-bots before it, the Finch was not in the spiral arm of a distant galaxy. 3 billion light years away from us, and 15,000 light years from the closest galaxy, it stood solitary in space. It was in the middle of nowhere and exploded between two galaxies. This was a huge blow to the leading theory. If these explosions really were the result of massive stars core collapsing, there's no way it would be happening in between galaxies. So it was back to the drawing board for researchers. They came up with 2 new theories to explain what could have caused the Finch to explode where it did. The first suggests that the Finch could be the result of stars being torn apart by an intermediate mass black hole. A black hole that has 100 to 10,000 times more mass than our Sun. Except the existence of these black holes has never been proven. Their smaller and larger relatives, stellar remnants and supermassive black holes, have both been confirmed to actually exist, but this middle child remains purely theoretical. However, should they exist, could they be responsible for this elusive light show? Astronomers have shown in simulations that stars can orbit intermediate mass black holes as many as 5 times before being ejected. With each orbit around the black hole, the star is effectively being ripped apart by losing more and more mass. Finally, the remaining stellar matter would be flung back out into the galaxy at speeds as high as 10% the speed of light. This would be consistent with the speed and brightness observed in LF bots, lending weight to this theory. One of the most likely places researchers would expect to find intermediate mass black holes is in globular star clusters in a galaxy's outer halo. Galaxies have halos that extend far beyond the main disk and bulge. They are most visible in spiral galaxies like our Milky Way. In our own home galaxy, the outer halo stretches some impressive 1 million light-years from its galactic center. Some scientists think that it is possible that the Finch could have been located inside a globular star cluster such as this. If this is the case, and intermediate mass black holes do exist there, it could be plausible that the Finch was caused by these unusually sized black holes ripping up large stars. The second theory researchers put forward suggested that the Finch could have been the result of 2 neutron stars moving towards each other in increasingly tight spirals until they collided. This kind of event causes a kilonova, which is known to be one of the biggest stellar blasts in the universe. One telltale sign of a kilonova is the presence of gravitational waves, which come through as a hallmark chirp caused by a rapid increase in frequency as 2 massive objects spin around each other, eventually colliding and merging. If we could find something like this when analyzing data from the Finch, it would lend strong credence to the neutron stars theory. However, as bad luck would have it, our chirp detector, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was down for maintenance at the time the Finch occurred. That means we don't know if such gravitational waves were emitted, as we have no data on them. One thing we do know is that no gamma ray burst was detected, which is something you might expect to see with a kilonova of this size. But remember, this explosion happened 3 billion light years away. That's really far, perhaps too far for whatever gamma ray data there might have been to be detected. All in all, none of this data can conclusively confirm or reject the neutron star theory. It's frustrating to bear witness to such an incredibly rare, new, and powerful phenomenon and not have the data to conclusively understand what is causing it. I guess patience is an underrated virtue for an astronomer to have, but they are not sitting on their hands either. Scientists are already planning to use the optics of the James Webb Space Telescope to carry out a search for any faint, globular clusters in the same location as the Finch. This would hopefully clarify if they are on the right path with the intermediate mass black hole theory. In the meantime, other researchers are focused on broadening the sample size. The more LF bots we can detect, the more we will learn about them. The 6 we have seen so far have taught us some things, but we have a lot left to learn. The only way we're going to get a larger sample is to keep sweeping the sky with wide field surveys like the Atlas HKO and the Zwicky Transient Facility. Scientists' hopes are pinned on the Vera C. Rubin Observatory, currently under construction in Chile, a telescope which will scan the entire southern sky every few nights, which I've done a video about here. It is expected to be operational by 2025 and will be able to capture 10 times more light than all previous facilities. Follow-up observations with Hubble and ground-based telescopes will help analyze more information, which could lead to more breakthroughs. LF bots are a super new phenomenon that we still don't understand well. Scientists themselves admit that the discovery of the Finch raises more questions than it answers. The more we learn about these bright blue explosions, the more they keep surprising us. All there is left to do is what hundreds of generations of astronomers have done for centuries before us. Point our telescopes up to the sky, watch, and wait. Was our universe designed to be hospitable to life? In a recent Astrum video, we saw that there is more dark energy in the universe than the energy from every single atom and particle of ordinary matter combined. Yet, everything we know about particles, fields, and quantum mechanics seems to suggest that this apparently large amount of dark energy could have been, and statistically should have been, much, much larger. Decades before astronomers even had any observational evidence for the existence of dark energy, physicists were shocked to see that the most successful theories of the 20th century predicted a level of dark energy so high that stars and galaxies could never have come to exist, let alone life and humans. So, how did the universe avoid this fate? And how are we alive to even ask these questions? I'm Alex McColgan, and you're watching Astrum. Join me today as we continue to learn about the effects of dark energy on the cosmos and explore the maths that claims we really shouldn't have existed at all. One of the first things you might learn in a physics class is that gravity is an attractive force between two objects, whose strength is proportional to each of their masses. Gravity keeps planets locked in orbit around the Sun. It keeps stars grouped together in the Milky Way, and it even attracts galaxies together to form galaxy clusters and superclusters. But if we zoom out further, this gravitational attraction begins to act in reverse, causing galaxy clusters to accelerate away from each other rather than drawing each other in. So, what's going on here? Einstein's theory of general relativity gives us a lens through which we can understand this strange behavior. In general relativity, space isn't just some background in which other things can move around. Instead, space itself can stretch and warp and evolve over time. Einstein showed that in this framework, gravity is no longer a force, but rather a distortion of an object's inertial path in a dynamical spacetime. For example, when a planet orbits around the Sun, in Einstein's description, it's merely following a straight line path in a curved space. This means what we observe as a repulsive force between galaxy clusters should really be thought of as an accelerated stretching of the space between them. But what could possibly cause the expansion of space to accelerate like this on the largest scales of the universe? To begin to answer this question, we need to know what causes space-time to stretch and warp to begin with. In Newton's theory of gravity, all objects with mass exerted a gravitational pull. And in general relativity, all objects with mass curve the space-time around them. But Einstein showed that in addition to mass, any form of energy or pressure will also influence the dynamics of space-time. Energy density is how much energy is found within a given volume, how much pop, heat, zap, and motion exists within a given space, and in our universe has always been found to be positive. Pressure is how much force over an area the contents of that space sends pushing into the rest of the universe around it. Think interstellar dust pushing on each other whenever they bump into each other in the void. As you can imagine, for objects so far apart, this pressure value hovers a little over 0 on a cosmic scale. When these values are cumulatively positive, as in the following formula, their influence on the space around them causes the space around them to contract in. Essentially, they create gravity by decelerating the stretching of space. However, conceivably, if you were somehow to set the values of this equation so that pressure was negative and greater than the positive energy density, that minus sign would cause the whole thing to flip, and you would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity, a dark energy. It's a little nebulous, as it's tricky to visualize anything with a truly negative pressure. How can you have less than 0 atoms in a patch of space, after all? But atoms are not the only thing that exerts pressure. After all, pressure is simply a force applied across an area. Fields can also apply forces. Think a magnetic field, dragging a piece of iron in towards a bar magnet, or two magnets pushing each other away. If dark energy was some kind of field that pushed away not just other magnets, but everything, then this would match what we see the universe doing. Vacuum itself having dark energy and enough of it to slowly, very gently push the universe apart. Scientists have thought a lot about dark energy over the years and have even figured out what its combined energy density and pressure needed to be to create the rate of spatial expansion that we witness. It's around 10 to the power minus 9 in SI units, which is a very small number, which is why we don't notice it here on Earth, and only spot it on the grand cosmological scale of the universe. This is actually good news, because it turns out that if the number was much higher or lower than this, things would get very bad for our chance of existing. Let me show you what I mean, with a quick sketch of the history of the universe. Here is the full history of the universe from the moment just after the Big Bang to the present. This is the dark energy density measured by astronomers. Scientists believe its negative pressure has kept this density roughly constant for billions of years. This is the density of ordinary matter in the universe, which has little to no pressure. The density decreases over time because the expansion of the universe dilutes the matter within it. Finally, This is the density of radiation in the universe, including photons and other extremely light particles. The positive pressure of radiation makes it dilute away even more quickly than ordinary matter. Towards the beginning of time, for a very short period, there were no atoms. Very quickly though, protons and neutrons fused together to create the first atomic nuclei in the very early universe. Shortly after matter took over as the dominant form of energy, the universe cooled down enough for those nuclei to attract and hold onto electrons, forming the first atoms of hydrogen and helium. These atoms were the building blocks of the very first stars, and these stars were pulled together by gravity to form the very first galaxies and clusters. Only later did dark energy take over, triggering the accelerated expansion of space and preventing the formation of larger structures. But what would have happened if the energy density were larger? Consider what would have happened if the pushing force of dark energy was stronger. It could have been enough to halt the formation of those early galaxies, pushing apart stars more powerfully than their own gravity could pull them together. A bit larger than that, and it would have been much more difficult for any stars to form either. And if the dark energy density were large enough, we would hardly have had any atoms or even nuclei produced in the universe. So that's what it could have been. What should it have been? Using some clever maths and the principles of quantum field theory, scientists attempted to predict how much the energy density of dark energy ought to have been. Their result was larger than the result we see in nature. How much larger? Their value came in at an astounding 10 to the power 45 joules per cubic meter. So, where does the predicted energy density of 10 to the power 45 joules per cubic meter fall on this graph? It's quite literally off the charts. If that prediction were correct, the universe today would have no structure, no features, no life. It would be a giant void filled with nothing but dark energy. And if the dark energy density were instead a negative 10 to the power 45 joules per cubic meter, the fate of the universe would be no more promising, as it would be forced to rapidly collapse in on itself in what's known as a big crunch. Scientists have attempted to account for their number being so far off by hypothesizing that there exists particles with positive energy and negative pressure, as yet undiscovered, that even out the maths and brings the answer for dark energy density back down towards zero. Perhaps there is some massive negative potential energy source that evens all the maths out, a cosmic stretched spring that somehow reins in all that rampant energy. Either that, or quantum field theory is fundamentally wrong. But as there's actually quite a lot of evidence supporting quantum field theory, it seems imprudent to completely throw the idea out. Instead, we are left contemplating the marvelous nature of this cosmic coincidence. What were the odds that the energy density of dark energy would be so low when it was predicted to be so much higher? That this great universal balancing act occurred in such a way that we weren't torn apart or crushed into a singularity. Without it being so low in magnitude, we wouldn't exist. Our very atoms would have never come together, torn apart by surging, expanding space. According to our predictions, we have got very lucky. This coincidence happened in such a way that the universe was able to produce life. So, was it a coincidence? The answer to that question strays from what we know for sure into what we simply theorize, however. It wanders into the realms of multiverse theory and mankind's quest to understand if we are not here by chance, but by design. There's a lot to cover, too much to cram into the end of this video, and so to do it justice, I've split this one into two. I'll cover the rest when I have the time to do it full justice. In the meantime, What do you think? Our existence so far appears to be excessively fortunate. How do you think it happened? Leave your answer in the comments below and see if other people's ideas match or contrast with your own. It's always good to hear from other viewpoints, particularly for a subject where there aren't clear-cut answers. You never know what you might find out. Our existence is surprising. Perhaps that means the universe has more surprises in store for us, if we can only find the answers. Are you feeling lucky today? You should be. If it hadn't been for a coincidence so great that it should never have happened in more than 10 to the power 56 universes, you would not exist today at all. According to our best physics predictions, dark energy density ought to have been high enough that stars and atoms would have been torn apart from its strength, unable to coalesce through gravity. Stars shouldn't exist, nor should planets, nor should you. As it happens, the actual density of dark energy is much, much lower, to the point that allowed us to exist, which is a fortunate coincidence, and raises the question, was this truly chance? Some argue this hints at the existence of a god, or an alien race so advanced that they might as well be gods, who created the universe and set its values in just the right way so that life would arise. But in physics, another theory has developed, one that says the best answer to this great cosmic enigma is the existence of multiverses. Does your being here prove that multiverses exist? Why do some physicists believe this idea? And what might other universes look like? I'm Alex McColgan and you're watching Astrum, and in the second part in this series, it's time to jump fully into multiverses, at least the topic of them. In our last video on this topic, we laid out the foundation of what is known as the cosmological constant problem. It notes that some force, dark energy, is prevalent enough that in our modern day, it overpowers gravity on a grand scale and is causing our universe to expand. This dark energy density is at a convenient level. If its density, tied to something known as the cosmological constant, was much higher or much lower, then our universe would either have been ripped apart by dark energy gone rampant, or would have collapsed down to a singularity due to unopposed gravity long before life had a chance to get going. The problem in this is that our quantum models predict that the density of dark energy really ought to have been higher. How much higher? Somewhere between 10 to the power 56 and 10 to the power 120 times higher than it is. That's more than a little off. That's so far off, it's been called the worst theoretical prediction in the history of physics. But the quantum field model is very correct in other ways, whether it's the double slit experiment with a single particle or the Bell equality test. Quantum physics turns out accurate predictions for some of the weirdest effects that we see in our universe. So how do we account for this discrepancy? Those of a religious mindset would point to the idea of intelligent design, that this wasn't so much luck as intent. A god, or extremely advanced being, has set the value of dark energy density to be just right for life to come into being for the purpose of creating us. Of course, this idea doesn't sit well with everyone. The existence of a god-like being by nature is difficult to prove or disprove, and taking such matters on faith is not really what science is about. For many scientists, a different sort of answer was needed. This is where multiverses start to come in. Let's go back to 1987, when the precise value of dark energy density in our universe had not yet been measured, but it was clear that it was extremely small, or zero, since, well, we existed, and so did everything around us. That year, physicist Steven Weinberg published a paper connecting the universe's fortuitously low dark energy density with something known as the anthropic principle. Essentially, the only universes that we can evaluate the probabilities of are the universes that met the right conditions to produce us. If the universe hadn't rolled such an unlikely roll of the dice, there would be no us to say whether these things were more or less probable. If it takes a massively unlikely roll of the dice to produce humans, then a universe where that roll of the dice actually happened is the only universe we could possibly see. Weinberg could be more specific than that. He was confident that the threshold of dark energy density for forming life would be no lower than the threshold for forming galaxies. In other words, by the time galaxies have formed, you've probably crossed the threshold to where life can form too. After all, how else was life supposed to arise if there were no stars and galaxies to provide complex building blocks and energy? At the time of his publication, observations of an extremely old and distant quasar had indicated that galaxies had already begun to form just 1 billion years after the Big Bang. Weinberg used this information to calculate that the formation of these ancient galaxies required the dark energy density to be smaller than around 10 to the power minus 7 joules per cubic meter. That meant that, assuming the galaxies were indeed necessary for life to arise, the threshold dark energy density for life to exist was less than or equal to this value, while not being so low as to be negative. Weinberg initially reasoned that if the dark energy density was significantly smaller than this value, something else other than anthropic reasoning must explain the dark energy density smallness. However, as we now know, the real dark energy density is closer to 10 to the power minus 9 joules per cubic meter, which isn't too far off from the threshold of 10 to the power minus 7 calculated by Weinberg. In short, life and dark energy density correlate surprisingly well. Of course, this ignores one vital point. Just because we can see universes where we exist doesn't mean it is guaranteed that we should exist. We could have just not existed at all. After all, the odds of the cosmological constant being at its recorded level is incredibly unlikely. Could the various contributions to the dark energy density have cancelled out to a value compatible with life just by chance? Probably not. Here's what would have needed to have happened. Just imagine generating 3 random real numbers between -1 and 1, adding them up, and hoping that the magnitude of the sum is at most 0.0000 with 55 zeros 1. It sounds just about impossible. But what if we had more than one go at it? What if we could generate those numbers over and over and over again until we got lucky? It might take us something like 10 to the power 56 tries, but given enough time, the unlikely cancellation of 3 randomly generated numbers will turn into an inevitability. We can use the same logic to potentially explain why the dark energy density is so bizarrely small. Instead of just one universe, imagine there exists a vast multiverse, with each universe having a different, random value for the dark energy density. Only a tiny fraction of them would have a dark energy density small enough to be compatible with life, but that's exactly where we humans would expect to find ourselves. This explanation requires no coincidences, no fine-tuning, no intelligent design, just a lot of different universes. On its own, the idea of a multiverse would still be too vague to be good scientific theory. For starters, what kind of multiverse are we talking about? How do they exist in the first place? Fortunately, there are actually a few different concepts of multiverse that physicists can describe. Firstly, we have a multiverse separated by time. If you are familiar with the idea of the Big Bang and the Big Crunch, you will know that it's often believed that this creation and destruction of the universe is an eternally repeating process, with new universes arising each time. If the underlying numbers of each universe are a bit different with each iteration, for instance if dark energy density can change from universe to universe, then with enough big bangs and big crunches, you could inevitably end up with a universe with a dark energy density exactly like our own. There are a few assumptions at play here, of course, as we don't know for sure that the universe does contract into a big crunch yet. But if it does, and if the rules of the universe are a bit different with each new iteration, then this is a viable model for a multiverse. A second multiverse described by physicists, although one I find personally a little bit more iffy, is a multiverse separated by space. While the rules of physics seem to be consistent across all of space that we can see, there are realms of space beyond our sight, sections of the universe that are accelerating away from us so quickly we will never see light from them. It's conceivably possible that the rules of these parts of the universe could differ from our own, and if this occurs, then we are essentially in another sort of multiverse. I find this model a little less satisfying though, both because it feels strange to call a further away part of our universe a different universe just because we can't see it, and also because there is no evidence that the laws of physics differ across space. This seems to me to be the least likely sort of multiverse. But finally, modern physics describes a third type of multiverse, one that is disconnected from our space-time entirely. In the many worlds interpretation of quantum mechanics, every macroscopic interaction or measurement of a quantum state causes the wave function of the universe to branch into multiple non-interacting parts. If you've heard of Schrödinger's cat, you can imagine the universe splitting into one universe where the cat is alive and one where the cat is dead. With every such interaction, the total number of universes grows exponentially, and the quantum multiverse becomes even richer and more diverse in its features. To be clear, we still don't know whether this branching process is the correct physical description of quantum mechanics, but it is arguably the simplest, and it is perfectly consistent with all experimental data. Or rather, we have no proof that it doesn't exist that way. If it does turn out to be correct, then it would add a whole new layer of complexity to our understanding of the multiverse. Multiverses are useful in that they remove the need for massive coincidences or intelligent design as a way of explaining our presence in the universe. However, are they actually real? Unfortunately, the answer is an unsatisfying "we don't know." While differing multiverses do help solve the cosmological constant problem, we actually have no evidence that they exist beyond the offering of an explanation for that coincidence. We have no proof that the laws of physics change across space or time or quantum universes. If other universes exist, they might have exactly the same laws of physics and values for dark energy density as our own, which would put us right back in the same problem we started with. How are we here when the odds of the galaxy itself existing is 10 to the power 56 to 1? And getting that proof will be difficult. We will need to either survive through a big crunch, or pass into a part of the universe that's so far away that not even light can travel quickly enough to get back from it, or enter a different quantum universe somehow. All seem impossible, or at least very difficult, and potentially the kind of trip you can't return from. This might be just as unprovable as the existence of God. So, in a way, you are free to believe whichever you find most comforting, or perhaps continue to wait until a better way of answering the question can be found. What is undeniable is that we are here. We live, we breathe, we can experience all the joys of life. However that came about, that's something to be incredibly grateful for. If we keep striving, perhaps we can one day discover the secrets to our origins. Whether we got incredibly lucky, did an all-powerful hand guide us into being, or was it the rolling of infinite dice that caused an inevitable result? Believe what you like. Just don't let it stop you from appreciating the wonders all around you. We don't need there to be a multiverse to appreciate this universe we're in, after all. There is much of science that we understand. If I threw a ball into the air and was given the right data about the forces acting on it, I could tell you exactly where it would land. Science explains through chemistry the molecules that make the ball up. We can predict the energy levels of the sound it would make when it lands. Much like a candle being held up in the dark, science illuminates our view of the world around us, but there is a limit to how far the light currently falls. Even today, when it feels like there is so much of the world and the universe that we can explain, there is darkness too. Answers we don't have yet, and worse, confusing results that erode our confidence in what we think we do know. There are experiments that seem to suggest that light is lying to us and call into question the very nature of reality. Are we real? Is time linear? Perhaps not. But are you ready for the comforting veil of understanding to be torn away, and for the strangeness at the edges of our understanding to be brought into the light? If so, I have some experiments for you. I'm Alex McColgan, and you're watching Astrum, and in today's Supercut, I will show you 9 experiments that will challenge your understanding of the fundamental laws of physics in a way that will almost certainly leave you with something between a headache and existential dread. You have been warned. And curiously, almost all of these experiments have something to do with light. Light is so much stranger than you might think. Sure, it may seem simple enough, traveling around the universe, delivering energy from one place to another. It helps us see. It provides life to plants, and thus to our planet generally. It has a reputation for being very fast. And yet, for a source of energy that has become synonymous with greater understanding, light is surprisingly difficult to understand. Light helps us see other things better, sure, but when scientists tried to look at light itself, it was surprisingly difficult. No, I don't mean that they started staring into any lamps. Please don't do that at home. But experiments in the last 200 years or so have proven that what light appears to be and what light is are actually two different things. The first experiment on our list highlights the following mystifying fact. Light behaves differently when you're not looking at it compared to when you are. But to understand that, let's begin with the basics. What is light? In the early 1700s, Isaac Newton theorized that light was made up of tiny little particles that he called corpuscles. But in 1801, nearly 100 years later, a man named Thomas Young discovered that light must actually be more wave-like than particle-like. He proved this using an important method known as the double-slit experiment. He set up a source of light and shone it through 2 narrow slits onto a board. Young noticed that rather than getting 2 bands of light on the other side of the slits, a strange striped pattern was forming. This was known as an interference pattern and was incontrovertible proof that light had been traveling as a wave. Why? Let's talk about waves for a moment. When waves travel, they oscillate up and down. But when 2 waves try to oscillate the same point in space at the same time, you get something known as interference. Imagine you had a bathtub with a rubber duck sitting on the surface. 2 waves reach the duck at once. One wave tries to raise the duck up. At the exact same time, the other wave tries to drop it down. What happens? Provided the waves are of the same magnitude and are perfectly out of phase, they will cancel each other out, and the duck would not move at all. This is called destructive interference. Similarly, if the waves both tried to raise the duck up at the same time, the duck would be raised twice as high. This is known as constructive interference. Because waves tend to expand in a circle, 2 waves next to each other will start to both constructively and destructively interfere with each other. Here are 2 waves in water. See these lines? These calmer patches are where the waves are cancelling each other out. This is the effect we see with light travelling through the 2 slits. As the light from one slit propagates, it cancels out the other wave of light at certain points, creating the interference pattern that Young noticed on the board. So the mystery was solved. Light was a wave and not a particle. Except, there is more to this experiment than meets the eye. Let's fast forward another 100 years to 1905. Scientists around this time had become puzzled by something known as the photoelectric effect. It turned out that when you shone a light on a metal surface, electron-like particles were coming off it. This was deduced to be because electrons in the metal were getting knocked off it by the increased energy the light was imparting. Imagine it like a fruit on a tree. If you pull the fruit off the tree, you need to use a certain amount of energy. Once the energy is greater than the strength of the fruit's connection to the branch, the fruit pops off. This was happening with the light and the electrons. Once the light hit an electron and gave it enough energy to pass the threshold, it broke free from the metal. However, what surprised scientists was that if you increased the intensity of the light, they had expected the electrons to be knocked away faster. If you pulled the fruit off the tree harder, it would come off faster. More energy equals more departing kinetic energy. However, this did not appear to be the case. Instead, increasing the frequency of the light increased the velocity of the departing electrons. The intensity of the light didn't affect the departing electron's velocity at all, but did affect the quantity of electrons being emitted. It was a bit of a puzzler. Albert Einstein was the man who solved the puzzle. He deduced that light must be traveling in little packets of energy, so sending more of them, increasing the frequency, was the only way to increase the energy going to the electrons. He called these packets photons, and later earned a Nobel Prize for his work. Light, it seemed, was more like a particle again. Or both a wave and a particle at once? Of course, even this is not the full picture. To be honest, we aren't completely sure about the full picture even now. Instead, we have more results that are contradictory. Let's go back to the double slit experiment. Armed with the knowledge of photons, physicists once again took a look at the double slit experiment. Experimental techniques had improved in the last 100 years, and it was now possible to emit a single photon of light at a time. So, the double slit experiment was done again. This time, only a single photon would be sent through the slit onto a detector on the far side. When this was done, the detector registered the arrival of the photon at just a single point. So, light was behaving like a particle again. But then, why had it interfered with itself in the previous version of the experiment? Scientists had an idea. They sent through multiple photons, one at a time, and plotted the result on the detector. And this is where the result became really strange. Once again, the detector started seeing the photons arriving at single points, one at a time. But bafflingly, the arriving photons started creating a pattern. It was the interference pattern, the proof that light behaved like a wave. But strangely enough, this was only occurring when a single photon was going through at a time. Somehow, the single photon, which was leaving the detector like a particle and was arriving at its destination as a particle, was apparently in some way traveling through both slits at once, enough to then interfere with itself on the other side like a wave. If light was just a particle, then when it went through the slits, you wouldn't see this pattern. You would only see two blobs of light, one for particles that went through the slit, and one for particles that went through the other one. And yet, here was the interference pattern with its multiple lines of light disproving that. Scientists tried to pin light down. They set up the experiment, but this time with two more detectors at the slit, so that scientists could observe whether it was indeed passing through both at the same time. It didn't. But at the same time, it stopped creating an interference pattern on the furthermost detector. And from this, scientists began to realize something. Light cared about being observed. To be clear, it didn't matter whether it was observed by a human eye or a machine. The moment light was interacted with in some way by any particle, which is the only way we can detect light, there's no other way to observe it, it started behaving differently than if it hadn't been detected at all. It was if light was snapping into focus anytime the universe asked it the question of where exactly it was, when without the scrutiny, it appeared to relax into something a little more nebulous. Bizarrely enough, to me, this seems to imply that light actually is more like a wave of probability rather than any discrete particle or wave. Anytime it was asked where it was, it confidently provided a definitive answer. It was at this point on the detector. It was not at any other point. But with no one checking up on it, light seems to be traveling in all directions at once, in accordance with certain probabilities. If you ran the experiment multiple times, you could quantify those probabilities, discovering that it was more likely to be on the bands of the interference pattern and less likely to be in the gaps. But anytime a single photon of light was asked, it gave an answer that was 100% concrete. This is highlighted through something known as the three polarizer paradox. Consider for a moment a pair of polarizing sunglasses. Obviously, these reduce the amount of light that can pass through them, usually by about 50%, depending on the type of lens and the wavelength of light. They work by being formed of thin chains of molecules that run lengthways across the lens. Any light that oscillates in the same orientation as this lens gets absorbed. Any that is perpendicular to the chains can pass through without trouble. The interesting case occurs when a single photon is passed through an orientation that's diagonal to the lens. In this case, you don't get half a photon going through. Apparently, you can't just absorb part of the oscillation that is parallel to the lines and let through the other part that is perpendicular. Instead, the photon snaps into either the one orientation or the other. It either is completely absorbed or passes through entirely, but now with a new perpendicular polarization to match what it would have to have had to have been able to pass through easily. How do we know that the photon wasn't this orientation all along? Because of what happens when you start adding more lenses. When you place a second lens behind the first, you can block out the light entirely, provided the two polarizations are perpendicular to each other. Let's say we rotate the second lens 90 degrees compared to the first one. Any light that gets through the first lens has a 0% chance of getting through the second, like trying to post a letter through a chain-linked fence. As a result, we see only black. But add a third lens and place it at a 45-degree angle between the other two, and bizarrely, light starts making it through all three lenses again. This may seem counterintuitive. How does adding more blockages increase the amount of light that makes it through? But this result actually rules out the possibility that the light has a fixed orientation. It must be snapping into focus at each new lens, rolling a quantum dice each time to see if it was the right orientation all along or not. If it makes it through the first lens, a 50% chance, it only did so because it was oriented perfectly perpendicular to the lens's polarization. Which means once it reaches the second, it's coming at it from a polarization that's diagonal. So once again, there's a 50-50 chance that it makes it through. It rolls a quantum dice again, and once again has a 50-50 chance of proceeding. If it gets through this hurdle too, then it again snaps to the new orientation, as if it were that new orientation all along, which it obviously wasn't. Which means that now it's polarized diagonally relative to the third lens, meaning that it now has a final 50% chance of getting through. Of course, some photons do not make it through all three of these probabilistic gauntlets. Only about 12.5% of them make it. But that's more than 0%, which is what was happening previously when you only had two lenses. Light likes to behave in discrete quantities. It is quantum. It seemingly snaps to a discrete value when observed, and honestly, we don't really know why. If you think about a wave, there is no reason why you couldn't simply have half a wave. You could half it again and again an infinite number of times and still have an answer that makes mathematical sense. And yet, it seems that down on a low enough quantum scale, you can't half light past a certain point. You can't have half a photon, or even 1.5 photons. And if you try to do so, the photon instead snaps to one or the other nearest integer based on probabilities, but only when it's asked. Otherwise, it's quite content to exist probabilistically, interfering with itself like a wave as it travels along, before jumping to an answer when later asked exactly where it is. What is going on here? This is still being theorized about. The closest comparison we have to it is something known as harmonics, where on a bounded string, only a certain number of waves can exist. On a guitar string, you can have one wave or two or more, but never a number that isn't a whole number. It seems that light works in the same way. Perhaps something pinches the beginnings and the end of the path light travels down, although what this might be and what mechanisms drive it are unknown as of now. Fundamentally though, perhaps the craziest thing about all of this is that this isn't just about light. Although we focused on light behaving like a wave and behaving probabilistically, all particles of matter do the same. Light is just another form of energy, and energy and matter are linked. Particles of matter, atoms, and even complex molecules have been shown to have wavelengths. Electrons are just as quantifiable and just as driven by probabilities as photons are. We are apparently all driven by probability if you scale things down small enough. So what is everything truly made of? What makes up energy and matter that causes it to behave in the way it does? What is going on under the hood of reality? Why is the universe behaving different when looked at compared to when not? And what does it imply to think that even you are on some level probabilistic? What this all means is anyone's guess. The person who figures it out will be the Einstein of our time. But for now, all we can say is that when it comes to reality, it seems the universe is playing dice. You and the world around you might be a lot less certain than you might have thought. So completes our first few experiments highlighting the strangeness of light. Take a breather for a moment. Give your brain a chance to unknot itself. From here on, it's only getting weirder. If there's one thing I've learned about light, it's that for unthinking energy, light seems to love messing with us. As I just showed you, scientists debated about whether it was a particle or a wave because it keeps exhibiting elements of both, seemingly unable to settle. Bizarrely, it behaves one way when you're looking at it, but a different way when you're not. But at least its speed is consistent. Light travels at the speed of light. No matter your frame of reference, that one thing remains the same. I have some bad news for you. It turns out the constancy of light speed might not be right either, and the next few experiments I'm about to show you proves it. Light might go slower than physics would predict in certain circumstances. And no, I'm not just talking about light slowing down in denser mediums like glass, although that's what I originally intended this video to be about. We have an explanation for that. I'm saying that in some circumstances, light seems to travel a path through time and space that has it either going slower or faster than the speed of light, even if dense mediums aren't present. But the really weird thing is that it ends up at the same destination in space and time anyway. Let me show you what I mean. Light travels at 299,792,458 meters per second. According to relativity, this is the only speed light can travel at, and interestingly, seems to stick to that number regardless of your frame of reference. Two people could be traveling through space, one at 1% the speed of light and the other at 50% the speed of light. But if they both look at the same beam of propagating photons, they will see them traveling at the same speed. Time and distance would seemingly rather warp than allow you to see anything other than light traveling at light speed. Of course, when scientists say this, they are only talking about light traveling in a vacuum. We've known for a long time that as soon as you get matter involved, light gets bogged down and travels slower. Light traveling in air only goes at 299,705,000 meters per second, a full 87,458 meters per second slower than light in a vacuum. Light in water goes around 225 million meters per second. Light going through glass caps out at around 200 million. The reasons for this are intriguing but fairly well understood, and certainly not physics breaking. When light travels through matter, its constantly waving electromagnetic fields gets the electrons within the matter to start moving, like ships bobbing on water. But as electrons moving up and down also generate an electric field that in turn creates a magnetic field, a second light wave is created by these moving particles that crucially overlaps the waves of the original light, albeit one that waves at a slightly different pace to the original light. Exactly what speed varies depending on the material. When two waves meet, they interfere with each other. They take an average, sometimes interfering constructively to build each other up, and sometimes working against each other. So when you take the grand total of all the ups and downs of each wave, you actually end up with a new wave, one that travels at a different speed to the other two, and one that goes slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you're left with just the original light again, which is then free to travel along its original path again, at its original speed, as if nothing had ever happened. Scientists have had a lot of fun with this concept over the years. Researcher Lene Howe at Harvard in 1999 was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1 billionth of a degree above absolute zero. 2 years later, Howe managed to slow down light speed to 0 before warming up the cloud and sending it on its way again. You might find that result surprising. However, strange things have happened in the opposite direction too. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that it exited before it had entered. While this might appear to mess with causality, how can you leave a building before you go inside it after all? Fortunately, there was a simple explanation that saved us from creating too many paradoxes. Although the light pulse traveled faster than light, the light itself did not. This was more an optical illusion than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. As Einstein showed us, each photon represents a tiny packet of waves moving up and down. The speed the waves inside the packet propagate is known as its phase velocity, while the speed at which the packet as a whole is traveling is known as the group velocity. You can also have a wavefront velocity, which is how fast the first photon in a wave of photons can travel. This is a little heavy in its terminology, so let's explain it with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's traveling quickly, but the crowd itself isn't going anywhere, so our wave's true speed is 0. These people are the group velocity, or possibly the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so and could keep doing a Mexican wave as they traveled. But although their waving hands might make the wave go really fast in the direction of their travel, it would vanish whenever it reached the front of the crowd. Information exchange couldn't go faster than the walking speed of the crowd itself, regardless of how fast the peaks in the wave seem to be traveling. Einstein in relativity never claimed that phase velocity couldn't exceed light speed. He just claimed that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving. Until the first person in the crowd arrives, no information can be delivered. Still, this difference between the waves within light and the speed of light itself will become interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the really physics-defying part. Let's think back on the double-slit experiment. There, researchers explored how light can sometimes behave like a wave and sometimes like a particle. However, in 2023, researchers from the Imperial College figured out a way to separate the slits of this experiment, not in space, but in time. The way they did this was simple. They took a transparent material called indium tin oxide that, under specific conditions, can be made to be reflective. Indium tin oxide is the stuff they use in most mobile phone screens. They fired a laser at it, and then rapidly changed the material from transparent to reflective and then back again. This left only a slim window, a few femtoseconds, where the laser was reflected. They called this a time slit. They recorded what the laser looked like after it had been reflected, and found that its frequency had spread out a little bit in the process, but other than that, nothing too crazy had happened. The weird thing was what happened when they sent two laser pulses through these time slits in rapid succession. The position of the emitter, the mirror, and the receiver remained the same. The only thing different was the time the lasers went through. Oddly enough, when two went through, an interference pattern happened. This was not an interference pattern in the same sense as with the regular 3D space double-slit experiment though. This was an interference pattern that had affected the laser's frequency. Certain frequencies of light within the laser faded out, exactly in line with the way intensity faded out in the regular version of the double-slit experiment. To visualize why this might be happening, let's draw out this experiment in regards to time. The time slit experiment can be drawn in a similar way to the double slit experiment, except we are going to need to visualize the change in the experiment over time. To do that, let's create a 4D graph where space is along the x-axis and time is along the y-axis. This is easy enough to do, it just looks like this. The photon leaves the emitter to the left, hits the time slit, is reflected, and arrives at the receiver. I've drawn this as a continuous line just to make things simpler later, but the idea works just as well either way. Later, a second photon is released from the emitter. It reflects and arrives at the receiver at a slightly later time, represented in how it takes place higher up, further into the future on our time graph. If light behaved normally, traveling along at the speed it was supposed to go at, this would be the end of it. Instead, light is interfering with itself. This means it must be traveling along a path that takes it through the other slit as well as its own. This is the only way that light could come in with the pattern that we see. And just like in the double slit experiment, it's likely happening on the other side of the slits too. As for why it's frequency and not intensity that's being messed with here, think about the implications of what you might see if light did indeed come in at a different angle like this. Photons come in little packets of waves, as I've previously mentioned. Now look at what happens if you change the angle at which those waves arrive. Here's how it normally might look. I've added a black timeline here and have highlighted every time the receiver receives a new peak in the wave. Here's what happens when you alter the direction of the wave's arrival. Suddenly, the peaks are coming in much more frequently. The frequency of a wave over time is very much connected to the color we perceive light to be. Lower frequency light is redder in color. Increasing the frequency shifts light's color towards blue. So this color variation makes sense. What makes less sense is what's going on with the paths this light is taking through time. Remember, the straight lines we started with represent the 299,792,458 meters per second that we see light traveling. So what can we say about the photons that are traveling along these paths? For some parts of their journey, they are traveling slower than the speed of light, taking more time to arrive at a destination that's the same distance away. And yet, for other parts of their journey, they are traveling faster than causality ought to allow. From their perspective, they are traveling backwards in time. As a reminder, these two emitters on the left are actually the same one, just at different points in time. The same for the receivers on the right. It is a mind-bending result. And yet, according to the results of this experiment performed by a research team at the Imperial College in London, this is what is occurring. The implications of this are startling. Light always travels the path of least time, the route that allows it to arrive at its destination along the path closest to 299,792,458 meters per second, the fastest anything in the universe apparently can go. And yet, it seems to me, in its efforts to locate exactly what path that might involve, light is testing the waters, putting out feelers that check to see if other paths, and seemingly other paths through time itself, might present a more viable solution. These feelers are interfering with photons that travel alongside it, but also with photons that travel a little ahead or behind it in time. To be clear, we never actually detect photons taking any of these other paths. We don't see photons coming in from the future. We never see photons traveling slower than the speed of light, provided there is no supercooling gases providing an explanation for why they slow down. And yet, for interference patterns to occur, to at least some extent, light must be trying out alternative routes through time. Perhaps it's like lightning, testing many different directions to find the optimal path for its destination before finding the one that works and collapsing down that path in one giant boom, all other feelers vanishing and collapsing. Or perhaps some other phenomenon is at play. Who can say? For now, all we know is that light has proved once again that it doesn't play by anyone's rules. At least, not rules that we can figure out. Again, now might be a good time to pause and reflect. This experiment we just saw hints that not everything in the physics world goes through time the way we might expect. Light might be playing a little fast and loose with the linear nature of reality. We are comfortable with causality, with the idea of things happening one after the other, and things in the past influencing things in the future, rather than the other way round. This last experiment could be interpreted as throwing a bit of a spanner in that. But sadly for our aching minds, it's not the only experiment to do so. Okay, break time over. Can information travel backwards in time? It's the sort of thing that would be really useful if it were true. You could tell your past self not to eat that burrito that didn't agree with you, or you could reveal to yourself the winning lottery numbers. But it just doesn't happen. The resulting paradoxes alone would make the whole thing laughable. In our universe, time always seems to flow in one direction, forward. The idea of traveling backwards in time, or even simply communicating with your past self, seems so outlandish, it can't possibly be true. So, why is it that on the quantum level, information seems to be doing just this? Alex, stop, you might be saying. You've already shown us that the solid universe around us might be nothing more than probability waves, and that light has some weird element to it that causes it to interfere with other light in its past and its future. But this? Surely it's impossible for information to travel backwards in time. I understand the sentiment. It goes against all intuition, and by all accounts, it doesn't seem possible. In previous videos, I mentioned that objects would require infinite energy to even go fast enough to reach the speed of light. So how could something go so fast as to reverse the usual direction of time and arrive at a destination just not instantly, but before they left? Not even light can do that, and it's the fastest thing we know of. Well, this rule about causality's speed limit seems to mostly apply to the macro scale universe. And by macro scale, I mean everything significantly larger than an atom. But down on the quantum level, time might be obeying different rules, or at least the speed of causality seems to come with some significant caveats. And to demonstrate this idea, we need to look at a man called John Stuart Bell and quantum entangled particles. I should apologize in advance for what I'm about to do to your understanding of causality. Okay, but what are quantum entangled particles? In quantum physics, it's possible to hit two particles together in such a way as to link them together, so that by measuring the one particle, you learn things about the other. For instance, if you know that the particles originally had a total of 0 momentum, and you learn the momentum of one of the newly quantumly tangled particles, you know the momentum of the other particle will be the exact reverse, making sure the total remains 0. Effectively, by measuring the one particle, you can learn things about the other. This works for other particle properties too, such as position, polarization, or spin. On the surface, there's nothing too weird about this. It's no different from me meeting up with a friend and discussing our plans for the evening. We agree to go out, and we agree that I will pay for the evening and my friend won't. Then, no matter how far we go on our night out, or even if at some point separate, I know I will be paying and my friend will know that he won't. This is how Einstein thought it worked, only it turned out that Einstein was wrong. Because as it happens, me and my friend did not discuss in advance who would be paying. And the strangest of all, we still both agree with each other anyway, 100% of the time, no matter how far apart we are. This is the strange thing about quantum entanglement, and quantum physics in general. We like to think of particles as having fixed properties. However, our penultimate mind-bending experiment shows that particles only have properties when you detect those properties. Yes, it's like the double slit experiment again, only that was focusing on a photon's position. It seems that particles are also kind of vague about the whole properties thing, instead only relying on probabilities as defined by a quantum wave equation. This doesn't make sense intuitively. Looking at a thing shouldn't be what gives it properties, right? Well, how would you know? If a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily. Let's talk about the Bell experiment. The maths for this is pretty complicated, but bear with me, it's worth the ride. The experiment was first conceptualized by John Stuart Bell, who wanted to know if particles really did have secret properties that they carried around with them, known as hidden variables, or whether they really were making some of it up on the spot. He noticed an interesting mathematical fact about the spin of particles. Before we go any further, I should probably mention that quantum spin isn't the same as normal spin. Misleadingly, quantum spin actually defines whether a particle is influenced, pushed or pulled, by a magnetic field. The name isn't important, but it is important to note that these particles aren't actually spinning and so can have different spin values in almost any given direction. Now, let's take two quantum entangled particles and let's say that we've arranged it so that their spin adds up to a total of 0 between them. This means that if one particle would be pulled by a field, the other will be pushed by it an equal amount along that direction, with the understanding that this doesn't tell you anything about their spin in other directions. One of the features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say up and down, it will have a 50% chance to be spinning up and an equal 50% chance to be spinning down. But remember, once you measure the other entangled particle, it will have a 100% chance to be spinning in the opposite direction to the first particle. On this fact alone, there is no way to tell if the two particles already knew their spin or are somehow deciding it on the spot and conferring it with each other now that they've been asked. But Bell noticed a clever thing by asking a clever question. If you measured two quantum entangled particles from two randomly selected directions, what are the odds that their spin for different directions would match? Now, let's define that at any time a particle is spinning towards a detector, its spin is up, and any time it is spinning away from a detector, its spin is down. What are the odds that both particles would be spinning up up or down down when tested? And what are the odds that they would contrast? Let's formalize this with a little experiment. Here we have two entangled particles with 3 detectors reading their spin in different directions. If particle A and B are both red with the top detector, then one of their spins will be up and the other will be down. They are entangled. This is what we looked at previously. However, if particle A is red using the top detector, while particle B is red with one of the other two, these two directions of spin aren't opposites. So particle B has flexibility in which way it goes. Quantum physics claims the particles are making up their attributes on the spot. So once you'd measured the spin of particle A using the top detector, it was a 50-50 whether the spin on the other particle using one of the other detectors would match or contrast. But this is not what classical physics predicted. Let me show you what I mean. Classical physics claims that particles each carry around secret information defining their spin in any given direction. So, for our 3 tested directions, each particle would have a value already. They aren't making it up on the spot. Let's say, hypothetically, our particle's hidden information states up, up, down for particle A and down, down, up for particle B, as B must be opposite to A for each of the directions 1, 2, and 3. Let's pick out a random detector for A. We select detector 1. Detector 1 tells us that A is spinning up. Now let's select a random detector for particle B. We select 1 there too. This detector gives us a reading of down. 1, 1, up, down. We can actually map out all the possible outcomes of this process of random selection in the graph. There are 9 possible outcomes if you were to only measure from 2 detectors at a given time. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on. For each of these possible selections, we have fixed hidden variable results that we know already, because we hypothetically defined them earlier. Let's fill them in now. Of course, if you detect particles using the same detector on both particles, you'll get a contrasting result because they're entangled. But we're not interested in these results. Classical physics and quantum physics both agree on this, so let's remove them. What are the odds that 2 different detectors for particle A and B will see the same result, and what are the odds they'll differ? Remember, quantum physics expected it to be 50-50. Particles are making up their values on the spot, and so it's perfectly random which they'll choose, as they aren't confined by the opposites rule here. But in this table, classical physics says that contrasting results only happen a third of the time. The other times, they're either both up or both down. If we do this many times, assigning different directions each time, and ignore exceptions, for instance, where the spins of the particles are all up, 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 or down, down, down. Once you crunch the numbers, the important thing to take from all of this is that according to the maths, classical physics predicts a matching outcome 55% of the time, while quantum physics continues to simply predict 50%. Pretty table be damned. This percentage difference was the key. By quantumly entangling particles and running this test over and over again, you could now see which percentage was correct. And it turned out the winner was quantum physics. Particles were just apparently making up their spin results on the spot, which is spooky. Because not only does that call into question our perceptions of reality itself, but that also means that the moment one particle decided on its spin result, its quantum entangled partner instantly knew that that decision had happened. You could test both particles at once, no matter the distance, and this same result would come back. Somehow, information had traveled from the one particle to the other in no time at all, far faster than light itself. So already something strange was going on here. This result disproved Einstein's predictions and showed that some information does seem to go faster than light. But we can take this one step further and have information going back in time. There is another experiment, our last experiment, known as the delayed choice test. Its primary purpose was to explore the fundamental nature of light, whether it was a wave or a particle, and to figure out when it decided to be one or the other. Unlike the double slit experiment though, this test was more about that last part, trying to identify the moment the waveform collapsed down into something discrete. In the double slit experiment, light seemed to choose a different path through space depending on whether it was observed or if it wasn't. In 2006, a number of scientists asked an interesting question. What would happen if you tried to observe the light after it had to pick a path? Consider this experiment. A single photon is sent into a beam splitter, with a 50-50 chance of either being allowed to carry on its way along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors, with both paths reconverging here, where the other beam splitter is inserted. Once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of the two detectors. If light were just a particle, sending a single photon into this experiment would give you an even chance of it arriving at one detector or the other. You'd not be able to tell which way it went, as the two beam splitters make that impossible to know, but you could see where it ended up. However, this does not occur. When the second beam splitter is present, the light produces an interference pattern, indicating that the single photon went down both paths, ultimately bumping into itself before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly behaves like one here. But what happens if you remove the second beam splitter? Suddenly, you know which path the light traveled down. If light arrives at the top detector, it must have arrived from path 1. If it arrives at the side detector, it must have come along path 2. And something about this knowledge spooks the light. It stops going down both paths, and suddenly, each photon only arrives at one detector. Here's the question. What happens if you insert the beam splitter after the photon has already started down either one or both routes? This is why the test is called delayed choice. If you delay choosing how exactly you intend to detect the photon, whether by knowing which path it came down, or making that ambiguous to you, what happens to the light? What happens is a very strange thing. When this experiment was performed, it was done multiple times, with the beam splitter randomly being inserted or not, but always being inserted after the photon had entered one or both paths. And yet, the results came back unequivocal. If the beam splitter was present, the photon suddenly and seemingly retroactively stopped picking a path. If the beam splitter was removed, the photon seemingly knew it would later be detected and picked a specific path to accommodate. Somehow, the beam splitter being added or removed in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other principle at play here that explains this whole thing, that accounts for the instant transmission of information between quantum particles, and allows it to be perfectly rational that light could travel down one path or both at the same time? Personally, I'm inclined to think that this is more likely. We clearly don't understand what is happening here, but it must be admitted, if we don't understand what is happening, there's nothing to say that causality isn't being ignored. In some way, maybe on the quantum level, time really is more fluid than it is up here in the larger universe. Maybe space and time simply do not apply down there. And maybe one day, someone will be able to come up with a theory that allows all these strange phenomena to finally make some sense. Until then, we'll just have to keep asking the same question. Can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is strange. Coincidences aren't always coincidences. Imagine for a moment a game of pool. The balls are placed in a triangle and the pool player lines up the shot. He shoots. The balls scatter, but then, against all probability, they all start falling into the same hole, at the same corner of the table. What would you think if you saw it in that moment? Are you likely to chalk it up to probabilistic fluke? Or perhaps some skill on the part of the player? Or are you more likely to start checking under the table that no one's done something to lower one of the legs? Some things in the universe are so improbable, they really shouldn't ever happen. Think now about our solar system, and imagine a large mass came screeching into it, large enough and at just the right angle for its gravity to wobble one of our planets out of its orbit and to scatter that hapless planet into interstellar space, like the balls on the pool table, but a whole lot bigger. What are the odds that that mass would knock out not just one planet, but two? And that those two planets would head off in the same direction at the same speed, enough that once out in interstellar space, they would start orbiting each other. The odds are astronomical, but I suppose it's technically possible. And so it's not a complete surprise that the James Webb Space Telescope has found an example of exactly this going on in the Orion Nebula. In the space between stars, two planets are orbiting each other. Each of them has a mass similar to that of the planet Jupiter, so scientists call them Jupiter Mass Binary Objects, or JUMBOs for short. But the Webb didn't find just one example of jumbos, it found 40, representing almost 1/10 of all the wandering planets that Webb saw in Orion. That's not just unlikely, that's downright suspicious. So much so that it's time to start checking the legs of the universe to see what's going on. I'm Alex McColgan, and you're watching Astrum. Join with me today as we investigate jumbos and try to find clues to explain just what might have caused such objects to occur so frequently in Orion. One thing scientists all agree on, our models for the formation of stars and planets are certainly wrong. But in what way is still to be discovered. Jumbos were first seen by the James Webb Space Telescope in October 2023, when it turned its awesome high-resolution instruments on the Orion Nebula. It's possible jumbos exist in other places too, but they have remained undetected for now, probably as their relatively small size makes them quite difficult to spot, unless you're using techniques like gravitational microlensing, which is in and of itself a highly randomized way of finding new planets. Gravitational microlensing, or seeing the momentary increase in a star's brightness due to the relativistic effects of an object passing in front of it bending more of its light towards you, is an event so unlikely that Einstein thought we'd never actually catch it happening in nature, even though he theorized it was occurring. While technology has improved to the level that we can actually take advantage of gravitational microlensing as a way of spotting new planets, mostly by developing some wide-angle telescopes, which you can watch a video about here, you still need a jumbo to pass in front of a star before you can see it. It's not surprising that relying on such randomness has left a lot of planets slipping under the radar. We need a powerful telescope like the Webb to give jumbos a proper look. But when we did discover them, they were a total surprise, one that no one in the scientific community had seen coming. The ones seen by the Webb are relatively young, only 1 million years old, compared to our own Earth's 4.5 billion years. But the strangest thing about them is how they orbit. Instead of orbiting happily around a neighboring star, or drifting through the vastness of space like most rogue planets we've discovered before, jumbos orbit each other. They are binaries, gently caught up in the gravity of the other at a distance of around 200 astronomical units, or 200 times the distance between the Earth and the Sun. Frankly, this is baffling. Binaries aren't completely unheard of in our galaxy. In fact, they are relatively common. About 1/3 of all the stars in the Milky Way are binary or higher, meaning it's quite natural for orbiting bodies to take this configuration. However, the smaller you get for the size of your star, the less this tends to happen. 75% of massive stars are binaries. 50% of stars the size of our Sun are. For smaller stars, this number drops to 25%, and for objects smaller than a brown dwarf, which aren't big enough to ignite into fully fledged stars at all, and are only around 15 to 75 times the size of Jupiter, it really shouldn't ever happen. Jumbos ought to be impossible. There should be no reason their frequency should suddenly uptick to roughly 1 in 10. And yet, that's what the Webb saw. When it surveyed the space within the Orion Nebula, astronomers were excited to spot 540 different planetary mass objects much smaller than brown dwarfs, and of these, 9% were orbiting each other in these binary pairs. 2 were even circling in a triplet, which is really rubbing probability's nose in it. 9% is an astonishing number at this scale of mass. As soon as scientists realized jumbos were this common, they immediately recognized that our models for the formation of planets couldn't be correct, as there are only 2 explanations for where jumbos could come from. The early days of a planetary system are always chaotic. You've likely seen artistic depictions of molten Earth in its early infancy, with comets and space debris raining down on it. This space debris was far more common in the solar system's infancy, when dust coalesced into rocks, then into asteroids, and eventually into planets with enough gravity to pull everything in around them, causing cataclysmic collisions along the way. Sometimes that gravitational pull was such that it didn't smash 2 objects directly into each other, but instead pulled them out of orbit and left them careening into deep space. This can even happen to very large planets if the circumstances are right. For example, it is actually theorized by some researchers that our own solar system used to have one additional gas giant, which was bullied out of our solar system by Jupiter, or possibly Saturn, although the smart money is on Jupiter. Jupiter's gravity was enough to tug on this other gas giant until it was sent spiraling out into interstellar space. We've asked on this channel before whether there might be a Planet 9. We didn't consider that Jupiter actually might have given it the boot long ago. Regardless, the idea of a planet being sent out into interstellar space, even a large planet the size of Jupiter, is not that extraordinary. Indeed, it's believed that wandering planets of all sizes are fairly common. There could be billions to trillions of rogue exoplanets wandering around in the void of space between planetary systems in our galaxy, which, if true, means there are more flying around out there than there are likely orbiting stars. But the sheer number alone cannot account for that 9% ratio, so something else must be going on. But the alternative explanation for the formation of planets doesn't work either. This second theory states that in the aftermath of a large supernova explosion, or through the force of solar winds, hot matter is sent flying in all different directions away from the center of a nebula. Cosmic dust pushed outward this way is also pushed together, helping it begin to coalesce due to gravity and form new stars. But if stars can arise in this way, why not planets? After all, to push enough dust together to make a star, you at some point will have an object the size of a planet, right? But no, not on its own. While this happens in the nurturing planetary disk of a newly formed star, it turns out that without that extra gravity, an aspect of gas physics stops this theory from working in interstellar space, or at least for objects of that size. It turns out that something called the opacity limit puts a lower threshold on the size of objects that can be formed this way without a star. They either come together to form, at smallest, a brown dwarf, or they resist coming together at all. In other words, interstellar dust and gas go big, or they go home. It works like this. All objects have gravitational potential energy. When gas coalesces together due to gravity, it loses that gravitational potential energy. That energy has to go somewhere, obviously, so in nature it tries to radiate away as heat. This is all very well and good when the gas is spread out, but once more and more gas starts gathering in, as you might see when gravity is pulling in material for a planet, then everything gets cloudier and cloudier, or more and more opaque. This actually makes it harder and harder for this heat to radiate away, so instead things stay hot and energetic. This pushes back on any more material coming together. A delicate balancing act is thus reached, where hot gas that cannot quickly cool down pushes back too hard against any gravity for any planet to form. Stars get around this problem by having a little extra oomph in their formation. There is a reason stars tend to form in nebulas. This vestigial extra push is enough to overcome the hot gas's dislike of pulling together. But once you push past that barrier, you already have too much oomph to form just a planet. Now it's a brown dwarf, or something bigger, or nothing. The opacity limit sees to that. Which is why scientists are searching around for an additional ingredient, something that might explain how a jumbo might still form in interstellar space. To me, this explanation seems like the neater one. If somehow you could overcome the opacity limit, you'd end up with planets naturally arising out of interstellar matter. If two Jupiter masses formed close enough to each other, they would drift slowly together and could quite naturally take up orbits around each other with no star required. Nothing about this relies on crazy probabilities, as the first pool table leg planet theory asks you to believe in. There could even be planets smaller than Jupiter masses out there doing the same thing. Two Earth objects, or even smaller, just too tiny to be caught in the Webb's camera. But perhaps an old theory can provide an answer. In 2001, long before we had any idea jumbos might exist, a researcher called Alan P. Boss published a paper in the Astrophysics Journal about the way objects slightly smaller than the mass of Jupiter could form from interstellar matter, provided that magnetic fields are active in the formation process, in effect jettisoning out the newly formed planet mass from the growing cloud that was about to become a brown dwarf, leaving the rest of the cloud to continue on its way towards collapse and stardom while preserving the smaller planet intact. The paper admits that it's conjecture and says that more work needs to be done to verify the idea, but I find it intriguing that the sizes in this theory match the reality of jumbos long before we saw them. Maybe jumbos weren't entirely a surprise after all. Is magnetism the answer to jumbos? It's too early to say. All we know for sure is that we know less than we previously thought. Jumbo's existence calls into question our models on the formation of stars and planets, and shows us more research is desperately needed. But then, that's half the fun of science. A theory is all well and good to have, but when you find something that throws off your theory, It's not a bad thing. It's an exciting discovery and an opportunity to get even better understanding of the reality we live in. What are jumbos? They are strange, Jupiter mass objects weaving a delicate dance on their own through space. But they might also be the key that unlocks our understanding of how stars and planets form in the first place. In 2022, astronomers using the Murchison Wide Field Array discovered a strange new radio signal that was arriving every 22 minutes. The astronomers were no strangers to such repeating signals. They typically come from pulsars, neutron stars which send intense pulses of light across the universe as they rotate on their axis. But as they began to look deeper into records of past observations, they realized this signal had been arriving at Earth since at least 1988, with remarkable stability, far more stable than is expected for a pulsar rotating every 22 minutes. If it was a neutron star, it was unlike any they had seen before. So, where was this signal coming from? I'm Alex McColgan, and you're watching Astrum. Join me today as we grapple with the mystery that lies behind this signal, which will challenge our understanding of some of the most awe-inspiring objects in our cosmos. The location of the source, named GPM J1839-10, is roughly 18,000 light-years away. Its signal arrives as pulses that can last any amount of time between 30 seconds and 5 minutes. These pulses can appear at any time in a window of just over 6.5 minutes, which is centered on 22 minutes after the previous pulse. To us, this may seem like a great deal of variation. 30 seconds and 5 minutes are very different durations, and the pulse arrival varying by over 6 minutes doesn't paint a picture of a very stable source. But neutron star dynamics can be very complicated, and if the source is indeed a neutron star, then many factors can affect the duration and arrival times of the pulses that we receive. Nevertheless, the astronomers were able to spot this signal hiding in data from the last 35 years and used this expanded dataset to average out the fluctuations. They calculated that the source was rotating once every 21 minutes and 58 seconds, as well as how much it had slowed down. But to their surprise, they calculated that this rotation period remained unchanged over the past 35 years, even though it is expected that the source will slow down as it radiates energy into space. We can only say for sure that if the source has slowed down, its rotation period would not have increased by more than 0.28 milliseconds over the 35-year period, because otherwise we would have been able to detect this in our data. This is an absolutely minuscule amount, and it shows that whatever the object is spinning with remarkable stability. This usually isn't odd for a pulsar. These are the timekeepers of the universe, the clocks of the cosmos, mechanistically ticking away with such certainty that we can use them to measure time across vast stretches of the universe. However, this level of stability is odd for a pulsar that is rotating so slowly. To understand what makes it odd, we need to recap how pulsars work and what makes them slow down over time. Pulsars are neutron stars, the leftover cores of dead supergiant stars which, barring black holes, are the densest objects in the universe. Planets like our own are made up of atoms, which consist of over 99.999% empty space due to the vast separation between the electrons and the incredibly dense nucleus they are whizzing around. But imagine an entire star made purely out of the neutrons that are found in the nucleus. No electrons, no protons, no empty space. Merely a teaspoon of it would have as much mass as 11 times that of the entire human population, all 8 billion people. A typical neutron star is around 35% more massive than our Sun, and squeezed into a sphere that has the diameter about as long as the island of Manhattan. To call it dense would be an understatement. For reasons still unknown to astrophysicists, the extreme environment gives rise to an incredibly strong magnetic field. What does this have to do with the signals we receive from pulsars? Where do the light waves come from? To answer this question, we need to understand a complicated process that gives rise to the signal, an exponentially growing shower of light and matter, all spawning from a single electron. Near the magnetic poles of a neutron star, an electron can be accelerated by the magnetic field and emit a so-called curvature photon, tangential to the magnetic field line. This marks, if you like, the start of a pulse. The curvature photon moves in a straight line until the angle between its momentum and the magnetic field line becomes too great. Once this angle reaches a threshold, the light dissipates and imbues its energy into the quantum field of electrons. An electron is created alongside its antiparticle, the positron. The electron-positron pair has some momentum perpendicular to the magnetic field lines, which they spontaneously dispose of in the form of synchrotron photons. These two synchrotron photons can each then produce another electron-positron pair after they reach the threshold angle between their momentum and the magnetic field lines. This process repeats again and again, exponentially increasing the amount of photons and electron-positron pairs created until the synchrotron photons no longer have enough energy to create electron-positron pairs, putting an end to the cascade. These photons then beam out into space, while the original electron continues its journey, generating more curvature photons and more cascades as it moves along the magnetic field lines. This pair production cascade is why the light of a pulsar is so intense that we can detect a signal from this tiny stellar remnant thousands of light years away. But why do we see this light as pulses rather than a continuously glowing beacon of light shining at us? This is because the magnetic poles of a neutron star are rarely ever aligned with its axis of rotation. Just like on Earth, the magnetic North Pole that our compasses point to isn't the actual geographic North Pole that Earth rotates around. So, the pulsars are like great lighthouses, sweeping their beams of light around the cosmos as they spin. And for an observer far away, like us on planet Earth, we see the beams sweep past us again and again as the pulsar completes its rotation on its axis. These are the pulses of light that our telescopes can detect. However, this is light with very long wavelengths in the radio part of the spectrum, meaning only a radio telescope can detect it. The light that the cascade produced is of the same wavelength, with the peaks and troughs of the light waves fluctuating in unison. The light waves are also polarized, which means they are all aligned along the same axis. This is a hallmark of neutron stars, and this is precisely what we observe in the 22-minute signal. The signal also has fluctuations that last between 0.2 to 4 seconds, where the axis of the light's polarization suddenly changes by 90 degrees, perpendicular to the original axis and then back again. This effect is yet another signature of the cascades at the poles of the pulsars. So much of our data points to a pulsar being the signal that you'd think this was an open and shut case. But one variable that we've mentioned earlier throws this entire theory into doubt: the slow rotation rate of the neutron star. Or rather, the combination of the slow rotation rate and the high stability of the rotation rate of the source. You see, as pulsars lose energy by shining their powerful beams into the cosmos, conservation of energy will ensure that the pulsar slows down. Eventually, the pulsar will slow down so much that it can no longer power the pair production cascades, and the light emission starts to shut off. The pulsar has entered the so-called Death Valley. This graph plots neutron stars based on their rotation period on the x-axis and the rate of change of their rotation period on the y-axis. Death Valley is shown in this grey band running through the middle, and any pulsar that has properties below this line should not be shining as the bright lighthouses they usually are. we see that our signal is below even the lowest line marking the Death Valley, meaning that if it were a pulsar, it should be well and truly switched off, and yet we are detecting it. Look at the cluster of other known neutron stars on this graph. They usually spin between 10 times a second to once every second. In comparison, our signal has a spin rate of once every 1,318 seconds, over 1,000 times slower than the typical pulsar. This would be fine if it was also slowing down quickly, which equates to moving this data point upwards on this graph above the Death Valley. Such rapid energy loss would power the pair production cascade necessary to light the beacon of the neutron star. Yet, the neutron star is mind-bogglingly stable, and it makes no sense that we can detect it. The astronomers who found the signal considered an alternative mechanism that might explain how a neutron star with such properties might have produced this light. Maybe the neutron star is a magnetar, a neutron star that has an unusually strong magnetic field, greater than 10,000 times the strength of the weakest neutron star magnetic fields. Magnetars are known to undergo starquakes, cataclysmic events that release the tension in the upper crust of a neutron star. These stresses are produced by the strong magnetic fields of the magnetar, as well as the slowing down of the magnetar rotation. A fast-spinning magnetar will bulge in the middle due to the centrifugal force distorting the star from a perfect sphere. As the magnetar slows down, the outer layers need to readjust to a new equilibrium and lose some of the bulge they have. The crust snaps into a new position, causing magnetic fields to temporarily realign and powering the release of the energy as light that we can detect on Earth. The most powerful starquake detected, that of SGR 1806-20 in 2004, released so much energy that if it had taken place as far away as 10 light years from Earth, it would have caused a mass extinction event. If something is able to light the beacon of a dead pulsar, it would be this. So, could GPM J1839-10 be a magnetar that has undergone a starquake? Have we resolved the mystery of the 22-minute signal? It seems not. We expect these starquakes to also emit light in the X-ray part of the spectrum, yet no X-rays can be detected from the position of the source roughly 18,000 light years away. It also wouldn't make sense for a magnetar outburst to be going on for 3 decades. The starquake is a temporary phenomenon, and the energy dissipates within a few years at most. It is simply incomprehensible that this signal would have existed for 35 years if it was indeed a magnetar. Once again, the unique properties of our signal exclude it from being a neutron star, even an unusually powerful one that has undergone a special event such as a starquake. But what else could the source of this mysterious signal possibly be? The astronomers who discovered the signal proposed a few alternatives for the identity of the source. One possibility is a highly magnetic white dwarf. A white dwarf is another type of remnant left from the recent death of a star, but one that didn't have enough mass to collapse the empty space in the atoms to become a neutron star. A remnant that has an unusually strong magnetic field could produce radio emissions, and as it is not a neutron star, it could get away with being as slow and stably rotating as the source of our object while doing so. The issue is, this would require an exceptionally strong magnetic field, greater than any we have spotted on a white dwarf. AR-SCO is the only known radio pulsar that is actually a white dwarf, and its radio emissions are 1,000 times less luminous than the source of our 22-minute signal. So, if a white dwarf is unlikely, what are our other options? Astronomers have observed low-frequency radio waves coming from the interactions between stars and exoplanets, as well as a binary of 2 brown dwarfs rotating around each other, but this emission is typically weaker, around 100 million times weaker than the source of our signal. In the end, it seems like none of our theories can explain the 22-minute signal. While the unresolved question about the source of the signal may feel frustrating, this is precisely the kind of mystery that astrophysicists look for. When scientists find new data that challenges our long-held theories, they can usher in revolutions in our understanding of the universe around us. Here, our already shaky understanding of neutron stars is being challenged. The astronomers are confident that the ease with which they identified this signal means similar sources lie out there in the galactic plane, waiting to be identified. Just like GPM J1839-10, the other signals might already be lurking in the data we have collected. Identifying more of these signals will shed light on the process powering emission beyond the neutron star Death Valley. Whatever lies behind the 22-minute signal, we are sure to learn of an entirely new phenomenon that we have never seen before. Isn't that exciting? What do you think could be the source of the 22-minute signal? Let me know in the comments below. Thanks for watching. This video was in part made possible by all the Astromnauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.